Never.
This is evidence of caramelization. Watch it. See. We have burning. I like them black, and apparently this causes cancer. That's how I like it. 1 dose of cancer, please. So I know it's been a while, but I just wanted to get back to teaching you guys some awesome chemistry and getting to see how chemistry actually relates and ties into the world around you. So I actually was at a cookout like 2 months ago with my friends, and we actually made s'mores, we grilled out, and we even grilled pineapple with some brown sugar on top. And I was super excited by this experience. It was really beautiful outside, and I got to smell the aromas of the grilling, and it got me thinking about the Malliard reaction, caramelization, and actually non-enzymatic browning. And today I actually want to focus in right on caramelization. Now, a lot of times when we think about caramel, we think about pralines, coffee, cakes, cookies, any of those things that have done some non-enzymatic browning. They actually also are having the Malliard reaction occur with them, but today I just want to focus in on the caramelization reaction itself. So bear in mind also the footage that you just saw with the marshmallow turning black. The actual blackened marshmallow parts are actually the product of carbonization, whereby an organic compound actually became ash because it released CO2 and water to the environment, and it was completely oxidized. So actually just focus in on the fact that the marshmallow turned brown in some places, and that's actually where the caramelization reaction is occurring. So that caveat aside, let's get into the actual chemistry behind this caramelization reaction that I was taunting you with at the grill out. In the caramelization reaction, you actually have sucrose as a sugar that can undergo something called pyrolysis, which is a chemical alteration in the presence of heat. And in an acidic environment, this is accelerated. So as you see here, I have my little triangle for heat to show that the sucrose is going to be chemically modified so that it falls apart in the presence of heat. And it's provoked because of the heat, but it's accelerated with the acid because the acid helps continue to the end products. So here is the fructose part of the sucrose molecule. As you know, sucrose is comprised of fructose and glucose monomers joined together with a glycosidic linkage through dehydration synthesis. So then when you go to break them apart chemically through pyrolysis, then you wind up with the fructose molecule receiving electron density from this bond. It's actually the nucleophilic electron density is going on to the electrophile. The oxygen being electrophilic because it's highly electronegative and it holds on to electrons very well. Then you get this intermediate that has a negative charge. Now in the presence of hydronium ions, which occur in an acidic aqueous environment, and we know that any atmosphere here on Earth usually contains some water. So the fact that you're heating it up in the presence of atmospheric water means that the water can help form the hydronium ion in the presence of acid. And we know that sugar tends to be in an acidic environment anyway. Like if you think about breads, marshmallows, coffee, things like that, they are already an acidic environment, and that's actually why they are acid forming in your body. So in the presence of the hydrogen ions, this winds up getting neutralized, and you end up having an intermolecular hydride shift coming from this carbon onto this carbon. So then you wind up getting your fructose molecule. You might be thinking, how on earth did you get fructose out of that with the stereochemistry being as it is? If this is pointed forward, this is pointed forward, this is pointed backward, and this is pointed backward. Well, it turns out that in the process of making the fructose in its long chain form, you actually flip across this bond, making that hydroxyl group pointing away from you now pointing at you. And then you hold this one constant and this one constant, and you wind up with the fructose structure. Now for the glucose molecule, it actually undergoes reaction with the water that you've made because the hydronium ion was broken up by the fructose. It actually comes in and attacks this carbocation that's formed when the electron density is pulled away from this bond. So the nucleophile now becomes this electron density coming in and attacking the electrophile, and you wind up getting a double bond between the oxygen here and the carbon here. And then you have water attacking this carbocation to form a hydroxyl group that you see down here. And you might be asking, again, how is the stereochemistry actually valid? Well, it's actually that the bond is being flipped here. So what was pointing at you is now pointing away from you when it's in its most energetically stable form. So that's kind of the caramelization reaction in its actual chemical form. Aside from that, it's just cool to think about when you're eating things that are like pralines, like s'mores, cakes, cookies. Any of those things have participated in caramelization, whereby a sugar undergoes pyrolysis to form its monomeric counterparts. And then the actual process of caramelization continues to form products like diacetyl, which gives caramel its distinctive flavor, maltol, which gives foods their characteristic bready flavor, esters, which give foods their distinctive sweet and or fruity aromas, and furan, which can be carcinogenic in large quantities but is a byproduct of this reaction. While it's true that sometimes caramelization actually stops right there with the chemistry that I showed you on the board, where we saw the breakdown of sucrose, a starch disaccharide, into its component monomers, other reactions can actually occur, especially if the starches are different. So in the case of other starches, you could have equilibration of anomeric and ring forms, you could have condensation reactions, intramolecular bonding, isomerization reactions between aldoses and ketoses, dehydrations, fragmentations, and other unsaturated polymer formation. So all of these things could occur just depending on which sugars and starches are actually involved. Hey guys, that's the video for today. If you liked what you saw, could you please give it a thumbs up and subscribe to my channel? You can also hit the bell to receive notifications when I post new content. I know it's been a while since my last video. I do intend to get back on a regular schedule, as I would really like to get to know you guys better and provide more content that stimulates your curiosity for chemistry in the world around you. Bye guys.
Okay, another byproduct of the Malliard reaction is that you get these really delicious s'mores.